For example, in aircraft, you optimize the wing for maximum lift to drag ratio, or you optimize the wing for minimal weight for the same load carrying capacity, things like that. Now, what has happened is the requirements have increased now. So you would like to optimize an aircraft wing to maximize its lift to drag ratio, at the same time minimizing its weight as well. So it's not multidisciplinary. It's not only aerodynamics now, it's also structures and other aspects. Start off with a couple of quotes. One from the Doyen of automotive industry, Henry Ford. He says that saving even a few pounds of vehicle weight would mean that they would also go faster and consume less fuel. Reducing weight involves reducing materials, which in turn means reducing cost as well. So there are multiple benefits of trying to optimize. For example, even simple thing as reducing the weight of an aircraft, car. Henry Ford talked about car. Now, this of course is far more impactful in terms of aerospace vehicles, especially aircraft or rockets. There's another aspect. This person is a philosopher, is a French philosopher, Antoine de Saint-Exupéry. He wrote in somewhere in 1900s that it seems that we reach perfection not when we have nothing more to add, but when we have nothing more to subtract from an object. Okay. For example, if you take a table, your table can have 8 legs, 16 legs, 32 legs, but that is not a great design. If you can design the table with absolute minimum number of legs, and that would be the optimum design, the real great design. What I mean by minimum number is just remove any one of the legs of the table would destroy the functionality of the table. For example, a tripod. You cannot remove one of the legs of the tripod and it won't work. Whereas if it's a full-leg table, you can remove one of the legs and it may still serve some amount of purpose. Okay, so this is the two aspects of optimization, why and how people are now looking at optimization. So before I go forward, a quick introduction to myself. My name is Narahari. I did my BSc at MIT Aeros in the Madras Institute of Technology. As I proudly say nowadays, I'm a junior for our ex-president of India, Dr. Abdul Kalam, and I'm senior to the present chairman of ISRO, Dr. Sivan. After that, I did my master's at Steel Institute of Science in Aerospace Engineering. 77 to 86, I worked on rocket propulsion at the Institute of Science. 86 to 96, I worked on aerodynamics at Aeronautical Development Agency on Tejas aircraft, which now you are seeing flying. 96 to 2003, IT industry. I worked in two companies. Actually, the second one was taken over by 2 other companies. 2003 to 2009, that is still retirement May 2009, I was technical fellow in the India Science Laboratory of General Motors R&D. From August 9, 2009 till date, I joined as MSR SAS. Now it is called MSR UAS. So it is a very simplified motivation for optimization. You would have seen that most people who have been doing some job for a long time in their life, they are very reluctant to change their ways and they are very reluctant to look at any new method of doing things. Of course, the depiction here is an old man and a young guy. And that doesn't mean to say that old people are not conducive to optimization or new thoughts. It's just a way of saying old means that he's been experienced as a wood chopper and he says, look, I got too much work to do, stop and listen to you. Whereas the young guy has a much better solution for chopping trees. Whereas the old man is using the traditional axe. So, outline of the topic. What is optimization and why do we need it? And we also have to go through some math background, especially that we cover objective functions, design variables, conditions for optimum, convexity, Pareto frontier, KKT conditions, and a couple of other things. And there are challenges in automobile engineering scenario, structural optimization, noise vibration handling, engine weight, combustion efficiency, and all that. Expensive time and cost and different solution methods. For example, finite element analysis, CFD, dynamic simulation, all of them are very, very expensive and time consuming. So there are some approximate methods called meta models or surrogate models. rigging and other things, which they have been used by different companies, including Tata Motors and some other examples. Some examples from open domain, largely from aerospace, is also going to be mentioned here. So engineering is well-established activities, including analysis, design, fabrication, sales, research, development of systems. So engineering covers kind of a whole gamut of activities. So the process of designing and fabricating has a long history. In fact, probably the oldest engineering discipline is civil engineering, closely followed by mechanical engineering. So the process of designing, fabricating has a long history. Many complex systems, buildings, bridges, highways, automobiles, airplanes, space vehicles have been built this way. However, improvements have been slow and costly, requiring substantial human and material resources. Therefore, systems have been designed, fabricated, used regardless of whether it is the best one. So what has happened is once they have found, let's say, a method of doing things and it has worked for quite some time, that goes into the handbook as design guidelines for the next generations to come. So improvements in improved systems have been designed only after substantial investment of time and material has been recovered from whatever they did earlier. So a classic case, for example, is if you design a mobile phone, which is 10 times faster than what is presently done and 5 times cheaper, you would not like to release it into the market immediately because your previous model you have spent a lot of money in research and development. Until you recover that, you will not release the new one. So this is the thing which has been followed. So only when they recover the investments, they go into the different kinds of methods. So we can build many systems to accomplish the same task. That is one of the challenges we have to face. Some systems are better than others. For example, you just want to cross a river. To cross a river, there are hundreds of methods. You can build a boat and cross it. You can build a bridge and cross it. You can make a canoe. You can make a ropeway. You can whatever. So there are different types. Several types are possible. However, to analyze and design all possibilities is of course very expensive in terms of cost and time. So based on previous experience and available knowledge, a design is selected and be designed in detail. So based on if the company has built bridges across different rivers or channels, they use the same knowledge and this new river is just a wider one or a steeper one or a deeper one or something like that. So they come up with the modifications of an existing design. So possible improvements are of course addressed, reduced fabrication costs from the last time they did. I could just give an example. When the first few sections of the Bangalore Metro were constructed, they had some issues. From that they learned and then they started making better in terms of time and cost. The second section, things like that. So also can you make the bridge carry more weight rather than whatever the older one? So we can set some targets within this time and cost or should carry this minimum load and cross the river with all that. So these are targets for your design or rather which will turn out to be later as some kind of constraints. Okay, so you have to build a bridge to cross a river of width, let's say W, within this time frame and within this cost. So optimization is not a blank check. They always have some limitation. So what do we mean by optimum? What do we want to improve and why? So objective function is what is defined, which we would like to go further in detail. Objective function is a measure of goodness, what we want to improve. And that enables us to improve or compare two designs qualitatively. So to take a topical example, now let's say there are multiple companies which have come out with vaccines. Okay, now which vaccine is better than the best? So what do you look at? So what is the measure of goodness in a vaccine? Measure of goodness in a vaccine can be 2 or 3 things. One, minimal side effects. Second, its efficacy. So if I am going to design another vaccine, I'll have to look at the existing competition and say, okay, my design should have minimal side effects as well as it should be more efficacy. So that's the kind of measure of goodness I want to improve. So this will enable people to compare 2 vaccines, find our vaccine versus somebody else's, and then decide what they want to do. And the difficulty here is we need to be able to estimate this measure numerically. You need to have a metric, a measure of saying, this is why I am saying this is better than that. We cannot have a qualitative things. So examples, we can say vehicle weight. For example, to carry the same number of passengers for the same range, my aircraft is generally 5% lighter than what is done by, let's say, Boeing or Airbus. Or the range it can fly, the same amount of fuel is better than that, or it's going to be cheaper. Or in case of car, the NCAP rating, the crash rating, or again in case of car, the noise vibration harshness is lesser than the competition. So if our goal is not right, a best analysis or optimization method is useless, which is the same old saying that if you don't know where you're going, what is the use of a map? Any map will do. If you don't know where you are, then all maps are equal. So we have to choose the right parameter to optimize. What exactly is it you want to improve? So it's really important to select a good objective function. The vaccine example, the efficacy of the, how far, how much, what percentage of people vaccinated does it protect from the disease? That is a good measure. Not saying that how fast it can be produced, what is the cost and all that. So they are important, but the really good objective would be its efficacy, followed by its side effects. So objective functions, may be linear or non-linear, or may or not be given explicitly. So this, of course, now we get slightly into engineering domain, in the sense that the objective functions could be linear as a combination of some things, or it could be non-linear and may or not be given explicitly by the problem or the customer or the requirements. So the next thing after the objective functions we need to look at is the design variable. So these are all, the basics I'm laying on the foundation for going into optimization. We talked about the objective functions. Now let's spend a little time on what are called the design variables. Design variables are also known as design parameters and will be represented usually by a vector x. Variables in this problem we allow to vary in the design process. For example, if you're looking at an automobile engine, we could be changing the bore of the cylinder, the stroke of the piston in an IC engine, or it could be in the sheet metal thickness and material in an aircraft wing. You may be going from metal wings to carbon fiber composites and an aircraft wing. You may be shifting one kind of material to another, especially in the gas turbine. So these are the things you can vary, which is under your control. So optimization in this case is the process of choosing the design variables that yield an optimum design. So you have to choose those design variables which give you the result you are looking for. Okay, so the design variables should be as independent of each other as possible. Only then you'll get a truly a good optimum. In this case, of course, the design variables could be continuous in the sense, for example, the example I talked about in the engine bore. A bore can be 90 millimeters or 90.1 or 90.2 millimeters and things like that. So that is a continuous variable. Okay, and the bore and thickness of the material also could be continuous, or it could be discrete. What do you mean by discrete? Discrete is standard size. For example, you can only have a spark plug, one spark plug or two spark plugs. You cannot have 1.5 spark plugs. So if you the design variables could be integers, design variables could be continuous. Now we talked about objective functions, we talked about design variables. The next thing we address is the constraints. Once the main requirements are met, design can be formulated as a problem of optimization, in which a performance measure is optimized while all other requirements are satisfied. Many numerical methods of optimization have been developed and used to design data system. Any problem in which certain parameters need to be determined to satisfy constraints can be formulated as an optimization problem. Once this has been done, optimization concepts and methods are quite general and in wide range of applicability in diverse fields. So there is no such thing as an unconstrained. So if you're, let's say, you're going to design and build a house for yourself, you're also going to have constraints like the time. I want this house to be built in so many months. I want the house to be built within this cost. I want the house to have 3 bedrooms and stuff like that. So these are constraints. You cannot optimize anything, whether an aircraft or a automobile, satisfying everything. For example, you cannot have a single aircraft which is the fastest, most inexpensive, efficient, and quietest. So there is no such thing possible. For example, this is a cartoon which generally shown in different kinds of design books. You have different concepts of airplanes designed by people who only look at them for their domain. For example, what you see here is a manufacturing person's idea of what is an ideal airplane. So he has a rectangular wings, he has a square cross section, and things like that. And this is a aircraft what is an aerodynamics person would like to have. It's only wing, there's nothing else. So if your person is looking at the noise produced by an aircraft, you would like to look at it this way. So then you are minimizing the vortex noise, and but of course, this aircraft would not be used for anything else other than reducing noise. So if you are looking at a finite element analysis person who is going to do stress analysis, he would rather have it this way. All cantilevers and beams and trusses, but nothing else. So obviously, none of this is a good aircraft. So you have to do something where you have a little improvements in all the possible things, but still it has to do the job. It has to be an aircraft which carries people or payload and be able to fly a certain amount of distance. So one quick example from a car. So let's say this is a generic car which was originally designed, and then you want to optimize it. Basically, optimization in this case is reducing drag. Let's say you are given a task of reducing this drag of this car so that it can take part in some kind of a race. It's just, there's no nothing numbers here, just as an example. So you modify, for example, if you see the gap between this motor compartment and the windshield is modified, and the rear part is changed, and all these things are changed. Keep in mind that the main objective is to reduce the drag. So now let's start getting to the brass tacks of the problem. So optimization problem statement is generally says that minimize a function. This is easier to state rather than maximize. Which is same as 1 over this. If we want to maximize, let's say the profit, I take 1 over that and say minimize. So minimize f of x by varying x. X is the design variables. Okay, don't bother about the symbols in a real domain and all that. It means that these are variables which you can change subject to some constraint. And some constraints, two types of constraints are there. What is called equality constraints. Okay, and in general, they are nonlinear functions or design variables. And you have inequality constraints. So what do we mean by equality constraints? We have to say that this should carry this many people. That's an equality constraint. And the inequality constraint should be, it should be not more than X number of newtons in terms of weight. So you can, it's not necessary that you always have one type of constraints. This is a generalized statement. Now the statement holds for whether you're minimizing the weight of a car or the range of an airplane, or maximizing the profits in a clothing store. Okay, so this is the formulation is same. Only the methods of solution differ depending on the kind of problem we are looking at. So if you look at optimization problem classification, this is a kind of infographic borrowed from one of the over domain things. Incidentally, whatever I've been talking about is all material from open domain. I make no claims of originality of whatever, whether explicitly or implicitly. I've just taken this from different textbooks, journals, papers, and using it only for purely educational purposes. So that there will be no misunderstanding that I am not making any claim to either having created any material here or not. Maybe the grammar mistakes and all that, that is my original contribution, if anything. So in this infographic, if you see the central part, optimization problem classification, so we can start looking at different kinds of things from the top. Okay, continuity. So are we looking at a smooth optimization problem or a discontinuous optimization problem? Is the optimization linearity? Is it linear or non-linear? Design variables could be quantitative, in which case could be continuous and discrete. Design variables also could be qualitative. Okay, so constraints. What are the constraints? Could be unconstrained, no constraint at all, or it could be constrained. So there will be some constraints which are there. And there is a little bit of math part here. It's called convexity. The You could be dealing with convex systems or non-convex systems. Down the line, I will touch upon what that means. And the data you have could be deterministic, meaning that it could be measured and you know for sure what the values are. Or it could be stochastic. Stochastic meaning it could be statistical averages and it could be changing in time. So this could be something, and it also have time, dynamic or static. So optimization problem classification covers the whole lot of things, the gamut of things. We will not, of course, be going to that. That will be a full semester course, and I may not be the right guy to be able to handle that kind of thing. But this is just for, as I said, an introduction to optimization. So this is what we talk about. So let's spend some time on trying to understand each one of them. I said linear and non-linear. What do we mean by linear and non-linear? When all objective functions and constraint functions are linear, we call the problem linear program. So all this, for example, in most of the engineering courses in the first or second year, LP or linear programming problems are solved. People are taught how to solve them. When at least one objective function or a constraint function is non-linear function of the design variables, we call this problem a nonlinear programming problem or NP. Okay, so generally linear problems are much easier to solve. That's why it's taught in the class, even in the second or third semester, I suppose. LP problems are much easier to solve than NP problems. So let's take this simple case. Minimize C transport C is the bunch of objective functions you want. X is the design variable. Subject to the condition AX is less than or equal to B, and A equal EQ suffix EQX is equal to B suffix EQ, XL is less than or equal to X less than or equal to. So these are the upper and lower bounds for the design variables. So you can say, for example, my material sheet metal thickness should not be more than 2 millimeters and cannot be less than 1 millimeter. So these are the upper suffix L is a lower limit, upper limit. So constrained and unconstrained, when the optimization problem is at least one constraint, we call it a constraint. Meaning that you cannot arbitrarily change the design variables. There are limitations to that. There are constraints to that. It's like, I don't know, very few people in the world will be able to call an architect and say, build me a house. And the cost is no constraint. That is not a possibility. Of course, when optimization problem does not have any constraint, we call it unconstrained optimization. Most practical problems are probably 99 of them that involve constraints. There are always constraints in terms of the material cost, in terms of time involved, in terms of people involved, a whole lot of things. Okay, so variable bounds may or may not exist, depends on the definition. So if X is truly unconstrained, X could be anything, no limit, from 0 metal thickness to 50 millimeter thickness. So such problems do not exist, but in math you can have them, and you do read how to solve them. And discrete versus continuous. If all design variables are continuous, we call it a continuous optimization problem. Any design variable is discrete, we no longer have a continuous optimization problem. Even one variable is discrete, then we have the typical issues. So typical cases, binary programming, the design variables are allowed to take only one of the values, 0 or 1, meaning that you either have a catalytic converter in a car to reduce the pollution or you don't have it. Okay, either you have a bypass in an aircraft engine or you don't have bypass. Okay, so this kind of thing. Or the other section is integer programming. Design variables are allowed to take only integer values. Now, how many engines an aircraft can have? It can have 1, 2, 3, 4 like that. So discrete optimization, discrete variables are allowed to take only given prescribed set of real values. X in nothing. So S is a prescribed set of values. For example, you want to go buy a ready-made shirt. What do? You go there and he'll ask you the size. It's 32 or 34 or 36 or 38 or 46. So that's it. You cannot say, give me 44 and a half or 37 and a half. They don't exist. Okay, so these are discrete but they have finite values. So you go to buy, you want to buy a trouser, it is 28 inches waist or 30 inches or 32 or 36. So this is what we mean by discrete variable. So if you have to optimize, then that is one thing. Binary is yes or no, and this one is number of 1, 2, 3 or 4. So these are the and sorry, if if an optimization problem has a single local optimum, because that's also the global optimum, it's called a unimodal problem. If an optimization problem involves multiple local optimum, one or more of which could be a global minimum, then we call that a multimodal problem. Let me do a quick demo what we mean by that. So if you have an object like this, you can clearly see that there is only one minimum point here. But if the solution space looks like this, where is the minimum? This has multiple minimum, which is the global minimum, which is the lowest point. You cannot really find out easily. You have to do a lot of things. So it is possible that the problem you are looking at has more than one mode solution, more than one minimum. Okay, so for example, if you look at this picture, you have two curves, A and B and C. Okay, A, B, C, all of them have only one place where they have minimum. They, of course, in this case, they happen to be in the same place. That is not what I mean. What I mean is this point is the minimum for A. Okay, for B, this minimum is ranging from here to here. And C, these are discrete things, then somewhere here is the minimum. Whereas, if you look at this point, f of x is where, this curve has two minimum. One is this one, and a better one is here. Okay, so when you are looking to arriving at this page, suppose you end up in this point, and whichever way you increase x small step size, you will find the value of x going up, f of x going up. So you may mistake it to be the real optimum, whereas the real optimum may be even better optimum solution may be there further down the line. So this is what we call a multimodal, and this is the global approach and local approaches, things like that. Single versus multiple objective. There is only one single objective to be minimized or maximized. We call it a single objective optimization. For example, you are only interested in increasing the range of an aircraft. Okay, that is a single objective. You are only increasing, let's say, the payload carrying capacity of a bomber aircraft. That's a single objective. Let's say you're interested only in reducing the fuel consumption of a car. That's a single objective. But sometimes there'll be more than one or two objectives. So you want the aircraft to carry the maximum range, also the maximum payload. So there are two objectives, not only range, now we are also looking at the load carrying capacity. Similarly, you want the car to have, let's say, a vehicle, any road vehicle, to have a minimal fuel consumption as well as as high an acceleration as possible. Well, that's what everybody wants, right? You want to buy a vehicle which will give you 100 kilometers per liter and go from 0 to 100 in 5 seconds. That's like, so that is two objectives. So generally now, with the advent of high-speed computers and better techniques and all that, people have now started looking at multiple objectives. Okay, we are still not come to the multidisciplinary. We are looking at multiple objectives in the same domain. Okay, so this is what is called the multi-objective. So, well-posed multi-objective problems generally involve conflicting objectives. So, if I want to have the car which can accelerate very, very fast, then of course it will guzzle fuel. If I want the car to be very frugal in fuel consumption, then it will be very slow. So that's what we mean by conflicting. You cannot have both of them. You cannot have a cheap thing or as good as the more expensive thing or more complicated thing. So what happens in such cases is you get a trade-off. What is the best among both of them? What's the best you can achieve with both of them? Not the absolute best in each one of them, but combined together, what would be the nearest you can get? So multi-objective optimization problems can be simplified into multiple single-objective optimization problems by aggregating the objective functions, by converting some of the objectives into constraints. So that is one of the things we can do. For example, in aircraft design, some of the requirements given by the customer in terms of, let's say, the rate of climb of an aircraft, or the sharp turn of an aircraft, or the load carrying capacity, or landing distance, and all that. They can be converted into constraints so that I don't treat them as objectives. I'm going to make them as constraints. Whatever I choose, these have to be automatically satisfied. Or sometimes you can combine both the objectives and form a different objective by giving some weighted things like that. So multi-objective problems are continuing. Many real-life design problems contain more than one design method, obviously. As I said earlier, car design means maximize fuel efficiency, minimize cost. Generally, in practical problems where multiple objectives need to be considered, the objectives tend to be conflicting, obviously. That is a given. Very rarely they are complemented. They will be conflicting in nature. So, example again, going back to automobiles, more fuel efficient cars, hybrid cars, or cars with regenerative braking tend to be more expensive than less efficient counterparts. So, similarly, if you want to reduce the noise of an aircraft, then you have to go and redesign the whole thing, and then that may conflict with something else. So in an aircraft, again, you want to reduce its radar cross section, and you go into all the design modifications from the stealth point of view. That will, of course, mess up your aerodynamic performance. So there is always a conflict. There is always a trade-off point, and a good engineer and a smart engineer will try to find the trade-off point, and then go ahead with that design. Multi-objective method in a methodical way to solve problems involving multiple design objectives simultaneously. That's the whole idea is. Okay, so let's say a problem, multi-objective problem example. Design a pinned beam with the following. Fixed beam features, its length L is given. This is a very trivial problem, just to explain what we mean by that. Length L, width B, the material and the load acting on it. The only parameter allowed to change is the height H. Okay, so minimize the bending stress in the beam. At the same time, minimize the deflection at midspan. So two design objectives. One, bending stress. The second, deflection. That is this part. Okay, the only design variable we have is height H. So this is a standard simple simply supported beam kind of problem. So that is just a trivial example. So generally, the multiple objective problem statement is minimize. In the previous slide, I had said minimize f of x. Now it's not f of x. It's mu of x, mu2 of x, mu3 of x. So it could go up to n. And this t is simply to write it horizontally instead of writing vertically. So don't get fucked by that. So multiple objective functions subject to gx. These are the vector of inequality constraints. H of x, a vector of equality constraints, and some other side constraints which are there. So when just n is equal to 2, we call it bi-objective problems. So now let's look at the bi-objective problems. Two objectives are there. And this is where we would like to introduce what's called a Pareto solution. Pareto solution is commonly employed now in engineering practice. And one of the interesting features of the multi-objective optimization is that the solution to the problem is generally not unique. Okay, this is the key point. Solution is not unique. A set of solutions called Pareto optimal solutions are the best trade-off solutions from the complete solution set of the optimization problem. For example, let's consider an unconstrained problem involving two design objectives, mu1 and mu2, which are functions of a single design variable, x. So we are interested in minimizing both design objectives simultaneously. So now let's say we vary the x and then first compute the one of them, mu, the objective 1, and then plot them as this way. This is the curve, let's say, and vary the design variable x and plot the objective 2. For some of you aerospace engineers, of course, this you should be able to recognize. This is the X would be the velocity, and this would be minimum drag velocity and minimum power velocity kind of curves. Okay, now that apart, let's leave that aside. So you have two. At this point, I have two positions here: M1 and M2. So when X is equal to M1, I have an absolute minimum of objective 1, this part, but objective 2 is very, very high. So the total is pretty high. Okay, and at M2, objective 2 is absolute minimum, but objective 1 is very high. So these points, M1 and M2, are called anchor points, and they are denoted by star symbols. Now, if you are trying to optimize and get the best trade-off somewhere between the two, it will be between these two things somewhere. So, moving from the objective 1 M1 to the right to a point B, in this case, what happens is the objective 2 will start reducing, but this will start increasing. Okay, so at the first look, this point where these two intersect, who is likely to be the value X, where you will get the best possible solution, where both are as low as possible, neither one of them too maximum. So this is just a initial intuitive guess. You can go ahead and compute and check that out. So to improve mu1, we have to compromise on mu2 and vice versa. This is the true for all points between M1 and M2. So such points are called Pareto optimal solutions or non-dominant solutions. So definition, Pareto optimal solutions are those for which any improvement in one objective will result in the worsening of at least one other objective. Because we are assuming that there will be multiple, at least one other objective will be destroyed or will be affected if we try to improve one of them. There's another way to plot that. So what this plot is called the Pareto frontier. Here you see the objective 2 is plotted by y-axis, objective 1 as x-axis, and the points M1 and M2 are also pointed. So when you have this curve, you see here this curve somewhere around this point where that arrow is there, you will get about the minimum of both. Okay, so from this point, if you go towards the right, objective 1 will increase. If you go towards the left, objective 2 will increase. So somewhere here would be the reasonable optimum which you can take if you want to optimize both of them together. So this kind of plots are called Pareto frontier. If the first thing, if you can find a Pareto frontier while you are doing optimization, I think it's like half the battle being won. So obtaining Pareto solutions, many objective optimization algorithms, including most conventional or classical algorithms, are suited to solve single objective problems. They have been optimized for that. You have different gradient optimization, this, that, and all that. Let's not go into that right away. So they're all suited for one objective function. So one way to solve a multiple objective by leveraging typical single objective algorithms is to combine all the objectives into a single objective function. Okay, let's say that the fuel consumption of your vehicle and the acceleration factor. So either you can give them all equal weight, saying that 0.5, 0.5, or you can say, look, I am more frugal, so I would rather give more weightage to fuel consumption and less to acceleration, or it could be the other way. So you combine together and then you come with a single variable which you optimize. Okay, so and you can say that if you're looking at crash safety, it's become very popular in cap rating and all that. So you can say that, okay, now that restrictions are there, safety is important. Well, cost is important too, but safety is more important. So weightage for safety is more as compared to cost. So if the single objective is optimized, this single objective, the Pareto solution is obtained. In some cases, I mentioned about deterministic and non-deterministic. There is no uncertainty in the variables of the criteria function of an optimization problem. Then it's called a deterministic problem. If there is an uncertainty of any of the variables, okay, then it's called a non-deterministic optimization problem. A common source of uncertainty is manufacturing tolerances. Okay, you may come up with saying that I'm going to use the bore and stroke of this engine. Some values you have derived with the optimal optimization, but it's possibly not feasible to manufacture because the number of the pistons made in the world are only have a finite number of them, and also there are tolerances which cannot be maintained. And the physical system cannot meet the right tolerances estimated by quantitative optimization. After all, if you have to manufacture it, you have to fabricate. Simple optimization will give you sometimes a very odd but very good design, but you simply cannot make it. Then it's not much use. So we'll stop here and continue with the math background in the next record.